This is the second video in the series about torque and rotational work. In this video, we're going to be looking at what happens when torque causes an acceleration, so non-equilibrium situations. So we're basically going to apply torque, which remember is the rotational version of force, in situations where I will have an angular acceleration, okay, alpha not equal to 0. So, just to reiterate, these slides are a repeat from the first video, but a net force is going to be responsible for causing an object to accelerate, and torque is R cross F, or basically the perpendicular force, perpendicular component of force times basically the displacement vector, or how far away from the point of rotation. Just to remind you, positive torques are going to be when the force generates a counterclockwise rotation, and a negative torque will be a clockwise rotation. Okay, so here's the picture and the various corollaries about force being perpendicular and farther from the pivot point. Okay, again, net torque, we just add up the various torques, paying attention to positive and negative, or counterclockwise and clockwise torques. Okay. And again, watch out for those zero torque situations. Okay, again, Newton's second law. Okay, F net equals ma, or in our case now, torque net is equal to I alpha. Okay, when the torques are unbalanced, the object will rotate or will have a rotational acceleration. Okay, if you remember F equals ma, then torque equals I alpha is relatively straightforward, as long as you can remember how the various variables change when we talk about angular activities. Okay, the method to solve these problems is going to be almost identical. Okay, we're still going to be drawing free body diagrams, and in particular, you're going to need to draw the force being applied at the point of contact. Just to remind you, the force of gravity does act at the center of mass for the object. Now, it's going to be important that we write both the translational F net equals ma equations and the rotational torque net equals I alpha equations. Yes, this is going to be lots and lots of equations, okay? But the equations will quickly reduce to your answer, let's hope. Okay, so here's an example. Okay, now I have a pulley with a moment of inertia I, radius r, and two masses on either side, m1 and m2. In the past, the pulley has been light, and the acceleration of the masses was given by the difference of the masses divided by the sum of the masses. The tension in the rope was considered uniform on both sides of the pulley. Now, tension will not be considered uniform, and we have to take into account the rotational action of the pulley. Okay, we will assume there is no slipping in the rope on the pulley. What that effectively means is that I can use those bridge equations that says the angular acceleration of the pulley is going to equal the linear acceleration of the masses, as long as we do acceleration equals alpha r. So, here's my free body diagram, okay? I start with the linear masses because that's what I'm familiar with, okay? So, force of gravity acts at the center of mass, tension acts at the top of the blocks, okay? So, and don't forget that we need to keep things subscripted because those are different variables. Tension is no longer the same, so tension will have subscripts now as well, okay? So, couple of other points. Okay, the string is still considered light and non-stretchy. If the string has mass, like if it was a chain or a rope, we will have to deal with the fact that the mass changes as the amount of string on each side changes. Okay, basically what this means is you can ignore, save a lot of calculus calculations. Okay. A non-stretchy string basically means that both blocks will have the same acceleration. So, writing the equations, I basically have tension 1 minus Fg1 is going to equal m1a. Okay, so object 1 will accelerate upwards, object 2 will accelerate downwards. Okay, and that's what I write for object 2. Tension 2 upwards minus Fg2 downwards is going to equal minus M2A. Don't forget that minus sign. That's minus sign frequently leads to errors. So if it helps you to draw the direction of acceleration, do so. Okay, always double check the direction of acceleration. Okay, so the hanging blocks have no rotational elements, so I don't need to write rotational equations for them. The pulley, on the other hand, does. So, okay, drawing the free body diagram. Okay, I've included the free body diagram for the axle holding the pulley in place, as well as the force of gravity acting on the pulley itself. Okay, besides those two, I also have the two tension forces. Okay, tension 1 for the first block, tension 2 for the second block, both at radius r, both perpendicular, and both straight downwards. Okay, I include the force of gravity and the upward force of the axle. They have no rotational aspects because they apply at an r of 0. Okay, and for this problem, it probably won't matter, but include them anyway. Okay, so translational equilibrium says my 3 down forces, tension 1 plus tension 2, plus the force of gravity on the pulley is going to equal the force of axle. Up equals down. Rotationally speaking, I only have 2 torques because the axle and the force of gravity act at a radius of 0. So T1R, okay, positive because that would make the pulley rotate counterclockwise, okay, is going to equal T2R. And that's going to equal minus alpha. Minus because I'm going to assume that the pulley, because M2 goes down, it'll make the pulley rotate in the clockwise direction. And clockwise is negative, so again, just like MA needs to be checked, I alpha needs to be checked for its direction as well. Okay, so in this case, it's minus I alpha, and everything is consistent in terms of the directions of the block accelerations and the direction of the pulley acceleration. So now I have all my equations, and now I need to figure out how to solve it. So here's my equations, okay? All 4, including the translational equilibrium for the pulley. Okay. So from here, I'm going to quickly get rid of the alpha. Okay, because I don't want to actually have to deal with alpha. They look like A's. The faster I can get rid of them, the less likely I'm going to make a mistake. So I'm going to swap out the alpha for acceleration divided by r. Okay, and so this is what I've done here. Now T1, okay, is also given on the first equation. T2 is given in the second equation, and I've solved those first two for T1 and T2 and made the various substitutions, though I have forgotten to include the R in both of these. Okay, so really I need to include R in these two equations. Okay, so, whoops. So I need to include R here and an R here. Okay, so solving that, I basically find that grouping all the accelerations on one side, I basically find that M1 plus M2, M1R plus M2R. Okay, so I need my R's in here. And my R is in here. Sorry about that. Okay, is going to equal effectively this, and I will need the R equations up here as well. Okay, sorry about that mistake. Okay, so now my acceleration is a much more complicated looking formula. Yes, that is going to be the case once we introduce rotational, but it still all works out. Okay, so slipping to non-slipping situations are also a type of rotational. But remember, when I have not slipping, I cannot use the bridge equations. Okay, so in this example, I have a ball that is given an initial translational velocity v, but let's say it starts with an angular velocity 0. So velocity is not going to equal omega r because omega is 0 and v is not. Okay, so kinetic friction between the ball and the surface generates a torque, and so the ball will have an angular acceleration. The ball will begin to spin up. Okay, at the same time, the kinetic friction will slow the translational velocity. Okay, at some point in time, the velocity v that started up here and slowly decreases because of friction, and my angular velocity started at 0 and it slowly increases because of angular acceleration. Okay, they will line up, and when they do, kinetic friction clicks off, static friction takes over, and it will basically stay in that not slipping scenario until we need to solve for something else. Okay, thank you. Okay, so let's talk a little bit about power, because the same energy concepts that we did for translational power also applies to rotational power. So remember that work is the change in energy or change in kinetic energy. So now work is also going to be represented by the change in rotational kinetic energy. So this is going to be the work done by a specific torque or the net torque. Okay, so we can also look at it as the integral of the torque integrated over the angular displacement. Okay, integral of force dx. Okay, in this case, torque d theta, and that's going to be equal to the change in kinetic energy as the object rotates. Okay, if the torque is constant, then the formula evaluates to nothing more than torque times theta is equal to your change in your rotational kinetic energy. And power is still going to be work divided by time. We have various definitions for work, including the integral form and the straightforward form and the change in energy form. Okay, but power is going to be work divided by time, or in this case, you could also look at it as torque times your average or constant angular velocity. So again, pretty much the same as translational, except we're talking rotational variables. Okay, thank you.